So I have been talking about techniques for reducing errors, call it quantum mitigation or quantum control, uh, whatever. There are various versions of it, but all of them assume that we know some properties of the noise, and in particular the direction in which disturbances occur, but we don't know the magnitude. And just knowing that this is the kind of nature of the noise allows us to take some countermeasures. So the last thing which I mentioned was the strategy implemented by this company called Q-CTRL and a description of what they do is available in this paper on the archive. Of course, the methods keep on evolving and there are improvements all the time, but it is enough to give you a kind of strategy how they are looking at the problems, and then keep on refining it to improve the accuracy. And what they essentially do in this paper is some version of the techniques which are called pulse shaping in the context of NMR. And here there are control pulses, and you design their shape to basically bring down certain kind of errors. So they have two kind of platforms which are accessible to a broad audience. One of them is called Black Opal, and this is essentially a graphical front end which will describe the logic circuit and where the errors can occur, and then what are the pulses you can apply at various places and so on. And that is essentially to give the introduction to the whole platform. The more detailed work is in the higher level module, which allows you to work with the design of the algorithm, and also it's execution. So these two platforms are available to a wider audience, essentially free. You have to register with a specific authorization system, but yeah, they have made it free at the introductory level up to a certain amount of usage. Of course, if you want to use it at a much detailed level, then you have to subscribe. And recognizing this feature that yes, there are a lot of things which can be gained, the framework which many people have used has been expanded to not just a sequence of fixed logic gates, but there is a new environment which is called open pulse, and in this environment you actually can design the shape of the pulse instead of using just some fixed logic gates. And this routines by Q-CTRL make use of this environment explicitly to design a kind of optimal algorithm. Okay. So this is just the background, and lot of tests have been done for simple algorithms, but they are all numerical. So unless you go and play around with all the parameters which are present, you will not really get an idea of what is going on. But I will give a broad description of what is actually done. So what they are aiming for is something called a robust control. What it does, it designs some control operations, or more generally, let me just write it in terms of Hamiltonian. And there is some unknown noise in the background. We know some properties of noise, some features which essentially give its direction. And what is the task is you don't want to cancel this at instant by instant, but you cancel the behavior of the two over a finite interval. Some choose some interval, whatever clock steps or something equivalent, and you will try to adjust these. Both of them are time varying functions. This one is under your design, this one is unknown, and after some evolution, this on the average kind of manage to cancel each other.
0 to tau, this is also time interval?
It's a time interval, yeah. The design, whatever it is, has to be done for this whole time interval.
So this is less than the time taken for algorithm to run?
The time over here varies inside this interval from 0 to tau.
After tau, it will stop.
After tau, you have to worry about the next pulse, whatever it is. But it's done step by step. Okay. Before you jump into this, there are several other conventional techniques which come into play because you are playing with this finite interval, not just instantaneous functions, and these things are available routinely. That there are so-called band filters, which essentially work in the Fourier domain. And the purpose of the filters is you remove certain parts of the spectrum, certain frequencies. And that can help by essentially what you do is project the signal into the Fourier domain. The part which are well understood, you can get rid of it before you start the rest of the exercise. And what is available kind of routinely in many systems that these things are used to suppress low frequency just fluctuations. Something which is varying very slowly compared to this time interval you are looking at. Because whatever you do is only applicable if the frequency is sufficiently high that something occurs within this interval, but there can be other things going on at a lower frequency, you project it out. High frequency words are the ones which are managed by this control pulses. Because this is a finite interval, high frequency can lie inside the interval, low frequency goes outside. Okay. So now you need to define fidelity of operations. So there are two kind of things you can define. One of them I will call operator fidelity over this time interval. So it can be defined by just straightforward projection, but I have to normalize it. So yeah. There is some target operation which you want to implement. Now, your control pulse will be limited not in the complete Hilbert space, but only in a finite frequencies or finite domains of the Hilbert space. And so you are not going to reach exactly the target which you are defining, but you reach its projection. So this is a projection operator applied into target to go into the smaller space, and how close that control reaches that. This is just an overlap, and this one is just for the normalization, and you take the modulo square to define the fidelity. It's basically just an overlap, but defined with all kind of
Projection operator is taking into which subspace? Projection operator is projecting into which matrix, which operator space?
These are operators, both the target state which you want to reach. There will be a corresponding operator starting from some initial logic. So if you draw a logic circuit, this will be just one of the gates. So this is the gate you want to implement.
So D is a function of U target. So projection is a function of U target.
Projection is a reduction of this U target to a smaller dimensional Hilbert space, because you do all kind of this frequency management inside it. Certain degrees of freedom are taken out from this overall operator, which is in the large Hilbert space.
So in this case, we want only high frequency components.
You want the frequency components which lie within this particular interval.
Why we are suppressing low frequency fluctuations?
That is the job of these band filters, which is you have real hardware available. There are lots of conventional systems. What they do is they essentially convert the signal into a Fourier domain, apply a projection into the Fourier domain, and then transform it back. But these are real hardware devices which are available, which are essentially these frequency filters.
What is the benefit of suppressing low frequency fluctuation?
The noise that you are trying to control is lying in the low high frequency domain, because you are only optimizing over a certain interval, but there can be noise in the low frequency also. These filters will cut it out. So the operator fidelity is one logic gate is how good the control design you have executes that particular logic gate. It's essentially evaluating that. And state fidelity, well, you can write two different things, which will require that in addition to the gate which you are applying, you are looking at the transformation of the state itself and how accurate that result is. So this is transformation in terms of where do you want to go. So there is some initial state. The control is a operator you have designed. Does it take you to the right final state or not? And the overlap of that will give you the corresponding fidelity for that particular state. can define all those things in a straightforward manner. What you need such functions for, these are the quantities which you actually optimize. Okay, so this if you get these numbers by construction, the maximum value is 1, and can design the whatever pulses you are putting in the algorithm, can take where you want to go, then you have done the job. And of course, to do that, there are lots of parameters sitting under the control. You have to keep on adjusting them. Yeah. Yeah, so maybe I wrote it the other way around. Yeah, it should be transposed. Okay, fine. After, yeah, when you act by control on the initial thing, it will give the final. Okay. So this is a kind of generic prescription. Of course, to simplify various things, the calculations are done in what is called as a rotated frame, and that simplifies the expression. So again, this rotating frame description is something which has been studied quite detail in the NMR technology, how you design it. And what it does is, it doesn't look at the expressions in the original system, but it looks at the expressions in a system which is transforming together with the control pulses which you apply. So I have to give a description to be precise. So the total evolution is governed by whatever control pulses you apply, and there is noise. And the evolution will be the exponential of this total Hamiltonian. What you do is you somehow subtract out this part so that you can focus only on the noise in the design, and that subtraction is called the rotating frame, in the sense that whatever is the evolution of this H control is, defines a certain amount of transformation in the Hilbert space, and you apply the inverse part of it to take it out, and what you are left with is essentially the noise, which you want to minimize. So it's obtained by, this is I'll do it, denote it by prime. You go to the rotating frame, and these are all functions of time. So is an exponential of all these things. So how does the rotated Hamiltonian look like? Well, it's a unitary transformation of the original Hamiltonian, and this U dagger and U take you to the frame where this control part is cancelled out. So if you write down the equation, the usual Schrodinger equation, so d by dt of it has
Yeah. Unitary transformation of H noise or H total.
what is
Unitary transformation
yeah, this is a unitary transformation.
of H Hamiltonian total or Hamiltonian noise.
Both of them are functions of time.
In the second line, there is no total Hamiltonian.
No. This is just a definition about if the initial noise Hamiltonian is this, in the rotating frame, what it will look like is this. And the original equation was the Schrodinger's equation corresponding to the total Hamiltonian. This is the standard thing. The total H is the transformation operator. And now I can write down what will be the equation in the rotated frame as well. And it can be integrated in a similar frame, but here I can write only the final version over a finite range interval. It's easier to label. Now that this is, I wrote it wrong. I have to cancel out the part which corresponds to control. So the total evolution of the original part was this u of tau. Because I went to this rotating frame, the control part of it gets cancelled, and what remains is this u prime of noise. And then I can look at all these expressions just as a function of u prime of noise when you are trying to these fidelities can be so that is essentially, well, it's a parameterization, but that is what you kind of achieve. And there are expressions I can write down. They look a little bit simpler. Because you got rid of this control from everything. So this F, now I have to put a prime on it. Okay. It will look product of, not product, projection. where essentially I got rid of the control, which amounts to replacing it by the identity operator. And this one state will also look similar, where there is no control left over here. So there is no initial and final. The control part is gone. The only stuff which is left is whatever this u prime of noise is. The purpose of this is to simplify the expressions which are going to optimize numerically. The point is that you don't know what is this noise and you don't know what is this rotating frame noise. They are still arbitrary functions, and you are just trying to optimize this particular quantities. So the simpler the expression you get, the better, and this is easier to numerically handle. Okay. So there is one feature which I mentioned last time and which is relevant, that this this quantum noise enters the dynamics multiplicatively. That is kind of buried inside this generic equation for the evolution, or even this. When there is a noise here, it multiplies the actual transformation. And this is related to the fact that all the expectation values which we calculate in quantum theory, they are bilinear in the state. Okay. So you construct a equation, the usual prescription of whatever, classical theory or quantum theory, doesn't matter. You take a Euler-Lagrange prescription starting from some Hamiltonian, and the Hamiltonian acts multiplicative on the state. The difference from the classical case is that the classical noise is additive. If you take the corresponding dynamical equation, say Hamilton's equation, you write x dot is equal to whatever, dh minus dh by dx, the gradient, etc., of the Hamiltonian, and then want to add the noise, then it's the gradient which gives you the force plus some other random force. Okay, so this is the difference, and it has to be maintained in whatever you design, and features actually change because of this fact that one case you want to remove the noise which is additive, other case you want to remove the noise which is multiplicative.
How to know what is quantum noise and what is classical noise?
you look at the evolution equation and ask if there is a perturbation in the Hamiltonian, how is it going to alter the evolution? Okay, so the classical equations and quantum equations behave differently. Hamilton's equations have one kind of feature, Schrödinger equation has another kind of feature. And there is now some question of how many parameters you are going to include in this control Hamiltonian which you want to design, and that is limited to what are the gates you want to put in the circuit. In general, you can write this equation in the full Hilbert space, but the actual circuit which you design doesn't have arbitrary gates. It has only 1 qubit and 2 qubit gates, nothing more than that, and large structure is generated by a sequence of these 1 qubit and 2 qubit gates. So what you are tuning are the parameters of the 1 qubit and 2 qubit gates in certain sense, and you don't worry about how good the overall picture is. That is defined by this final fidelity, but they are not your control parameters. Okay. So there is a, say I have m qubit, then there are large number of possibilities, just the 2 raised to m dimensional Hilbert space, but the 1 qubit gates which appear in the circuit, there are only m, and 2 qubit gates are, well, you can look at all possible pairs, and that is half of m times m minus 1. So the total, you can add up all those things. M is common to this is actually not m but 2m. There are 2 directions you have to choose for 2 non-commuting operators. The 1 qubit has x, y, and z, and you need at least 2 of them. The third one can be generated from it. So you write it in terms of x and z, and I think now I think the counting is correct. Okay, fine. So these are the generic gates which will use in the circuit. They will have their parameters which are designed by this control criterion, and using these gates you will evaluate this fidelity to get it to as large value as possible. The point is that the whole structure of the Hilbert space has too many parameters, and This is a unitary thing. It is the dimension of the Hilbert space square minus 1. So it is some number like 2 raised to 2m minus 1, just too large. You don't want to optimize your program in such a huge dimensional space with large number of parameters. You will tune it in this small number of parameters and see how well you can do the job. Otherwise, the whole exercise is hopeless. It just grows up exponentially, and you don't do that. And the optimization which is done is carried out numerically, evaluate, for example, this gradients of the fidelity to maximize it. This is one way of and dealing with it. And if you don't want to calculate the gradient, which has to be done numerically by changing whatever parameters you put in inside this control structures, it takes its own effort. And these days there is a kind of automated bypass available, which is machine learning. So you want to train various parameters. There is a certain function which has to be maximized, that is the fidelity. You give it to a neural network which will play around with the parameters and give you some answer. So what is known as this so all those things are buried inside this Q-control framework, how they will calculate the gradient or use deep learning technique, and you will optimize the fidelity, and that will be the what you call desired shape of the pulses to do the particular job. So that is the kind of structure. Now they carried out various sample studies, and that is the interesting part. So why all these things are worth playing around with. Or rather one mind. The words I'm going to use, how far away this thing is from 0. Therefore, systems which are about 10 qubit, you can improve this probability of going wrong, or rather suppress it by orders of magnitude. And this is what is the selling point of what Q-control has done. that you can take the existing platform, you shape these pulses, and instead of getting something accurate to say 99%, you can make it now 99.9%. Change by order of magnitude, and that is a big step, and available for both ion trap and so the libraries, whatever they're available for both the systems, ion trap and superconducting qubit platforms. And well, they are selling it to whoever wants to run any large-scale simulations of this kind of stuff. So this is a sort of philosophy, but it's a hybrid philosophy in the sense that a lot of work which is done here is actually carried out classically. So all optimization which that is a point, it is done in advance before you try to figure out what system you want to optimize, and when you use it dynamically. So the routines are there, find all its parameters classically, and then you implement it directly when the algorithm is running in the quantum operations with all the appropriate values of the parameters. So this is the same strategy which is also popular in the NMR machines, that all the pulses are designed in advance, and then you run the quantum experiment, which is controlled by a classical workstation. So the classical workstation gives all the instructions about what to do, and the quantum evolution runs accordingly. And well, it works, but in this sense, it's hybrid. It's not just completely quantum techniques. You have done a lot of part in the background and taken advantage of what are the known techniques from classical optimization and implemented it. And this remains a generic feature in many algorithms, because nobody really knows how to do optimization in a quantum sense. The methods which are used to minimize something, calculate gradients of something, they are all classical techniques. You don't really have its a good quantum analog. So that now brings me to the next topic, which I want to emphasize: how to do good optimization in the quantum domain. And there are lessons here. So there are something which we have seen before in a very different context, but the ideas are something which you need to keep in mind, that you want to make your algorithm inherently stable against noise, and what are the kind of features which you should then pay attention to. And the most important feature lesson in this is that avoid any calculation of gradients or small step evolution if you are looking for a robust quantum algorithm, because noise is going to perturb the small quantities, and if they get into the dynamics, you don't know where you are going to land up. So examples, things are something which I have described in the previous course. If you want to apply 1 qubit rotation on a certain qubit, do you actually do the geodesic evolution along the Schrodinger equation? No. What you do is write the 1 qubit rotation using the Euler angle decomposition, which basically can be done with only 3 finite step transformation, and then the accuracy or the robustness is much better. Instead of trying to integrate the Schrodinger equation, which will give you the geodesic evolution on the block sphere, but the uncertainty in that adds up quite fast. The other example which we have seen is Grover's algorithm. It uses what are called reflection operations. And not the small step evolution. Reflection operators are actually as large a step as you can take, with the constraint that magnitude is constant. So you don't want to go again from the initial state to final state by taking small steps, which is the answer you will get if you use the Trotter formula. but here you end up using Trotter formula with a large step, whatever it is, and it does a much better job in terms of giving the stability to the algorithm. Small step algorithms can be done, but they are not robust in the same sense. And the third thing is actually what I want to describe in more detail, and that is a recent development that what you do for the variational eigensolvers. See, the point is the same. These variational parameters will be something which need to be tuned. Question is how we are going to tune it, by changing them slowly as conventional classical methods will do, or you find large steps changes and get to the answer. And the point is that even with these variational eigensolvers, you can find a solution with large steps, and it is far more efficient. Okay, so what is the task over here? Let me put in some notation that the parameters are encoded in the wave function itself. So as some psi some state, there can be many parameters, some theta I. And these are the ones you want to find the optimal value. What is the object or the target? Here it was fidelity. In variational things, it is the Hamiltonian expectation value. So this is H, and it can have many components. I will just write so the Hamiltonian can have many terms. I wrote them as some weights times some operators. These weights I have kept outside just to normalize these various parts nicely. But because it's a quantum system, various HKs which appear here need not commute. Okay, one can be kinetic energy, potential energy kind of thing, or they can be different polymetrices, whatever it is. There are multiple terms, and what you have is a total result like this, and it has to be minimized by varying all these parameters which are there in the wave function. The point is that the Hamiltonian does not depend on the variational parameters at all. It is fixed. Once it is given, it is there. And now I want to generate various possibilities of this object and find out where is the best solution. So in general, well, this psi theta is going to lie in some huge Hilbert space. If there are m qubit system, there are dimensionalities of 2 raised to m. We are not going to search for all of them. it's too big a job, there will be too many parameters. But what we know is that any psi theta from some initial state by using only 1 and 2 qubit gates. So that we know in a general analysis, that is how we came down to doing only local operations in the Hilbert space. You are not going to search for all the dimensions. You will write whatever transformation you want to implement as some sequence of 1 qubit and 2 qubit gates. And by using many of them in some order, you can generate whatever states you want. Okay. So this is a place where you get a huge advantage. Okay. Where does the advantage come from? That you ask explicitly, what are these 1 and 2 qubit gates that you will implement in a circuit to generate arbitrary transformation? And the answer is quite simple. What we used, 1 qubit where only rotations about arbitrary axis. You can chase any axis in the block sphere and you give angle of rotation, and that was the 1 qubit operation. There was nothing more complicated than possible, and these rotations, the axis and the angle were variable parameters. Okay. So this contain what all this theta and the variable parameters. But two qubit gates which we use, they are very simple. It was either C0 or these days some people use control Z in certain circuit. But the point is, there are no parameters in there. It's a fixed transformation. So that means all this stuff which you are looking at as a variational parameters, where it is going to end up, it is going to end up in 1 qubit rotations.
So here, there in parameter section, you written two qubit gates half and minus 1. Here, there we were counting them as parameters here. There we were not talking about C0 gates. Yes.
It was there, the analog of that C0 was also there. But it is not the same problem.
There they considered as parameters. There they considered as parameters.
Yeah, if you want to tune all the gates in this control, the C0 gate will also be reshaped according to a different pulse. I'm not looking at the pulse shaping part in this particular analysis at all. Okay. I'm looking at what do I need to do to optimize this particular function in terms of the standard gates which are part of the circuit. And now this structure offers a huge advantage, that I'm varying the parameters, I want to minimize this quantity, but the only place where the parameter goes is in 1 qubit rotation. Okay. And the answer is, well, quite remarkable. What do I need to do to find optimal value of the angle? For that, let me define the generic rotation. 1 qubit is exponential of minus I theta by 2 sigma dotted with n. Standard convention, and you can write it as cos theta by 2 times identity minus I sin theta by 2 times sigma dot n. And I will write also this generic function where, let me write it in the same notation. That this is some unitary operator involving all various parameters acting on some initial fixed state. And there are, well, many of these parameters can be present depending on how many of these gates I want to apply in the algorithm. But the important fact is that these are all 1 qubit rotation. So if I want to focus on only 1 qubit at a time or 1 rotation at a time, I can always rewrite it as this is I want to focus on one particular gate, call it theta j, which I want to tune. There will be a lot of stuff before, lot of stuff after, but point is that this V and W which I wrote, they don't depend on theta j. There may be other parameters sitting inside it, but any generic thing can be broken up if I want to look at only one particular parameter which is in one particular gate. And the job is now to, can I solve for this theta j cleverly? Okay. So Well, I take this expression and plug it in. I want to minimize this, but I am looking to minimize only for, say, theta j and leave other ones as they are. Of course, you have to cycle through all the parameters which you optimize in one by one and hope that it will converge at the end or something like that. But let us just look at one of them. So what is this expression that the total Hamiltonian, as I wrote down, I have to now substitute for this psi theta I, this u times psi 0 and all these things which go with that. So there is a k, wk, these things don't matter. Then there is a psi 0 and then there will be a complex conjugate of this, which will be wj dagger. R dagger is nothing but minus theta j, and then v j dagger. That is one part. Then there is a hk, which doesn't depend on theta j, and then there is a v r theta j acting on psi 0. I just wrote down everything in detail. Okay. So now we can ask, I want to optimize with respect to theta j, and that appears only in these particular factors. Everything else is independent of theta j. So all these three things, they are independent. And they can be whatever new notation you can introduce. It doesn't really matter. What I want to now do is, I know this form explicitly, so I will expand it out. Okay. So what will the expansion look like? Let me invent some notation to keep this thing loud. So W acting on psi 0, let me just call it psi 0 prime. Okay. Then this is cos theta by 2 plus I sin theta by 2 sigma dot with n. Then let me call this thing h prime, well, it's k, and then another factor of this. There is an identity here. Okay. So all these factors which don't depend on theta, I just have put in new expressions which contain primes. And then it can be multiplied, everything. So this time this will give me cos square theta by 2. And the rest of the stuff is all independent of theta, whatever this weight is there, psi 0 prime, hk prime, psi 0 prime, it will give me some expectation value. Whatever it is, it's well, it will be a real number because this expectation value is of a Hermitian operator. So let me give it some name. Okay, so it will be some a k, which is psi 0 prime, hk prime, psi j together with all these things, and times cos square theta by 2. Then there is a term which multiplies these things together. It will give a matrix element of psi 0 prime. Then there will be a sigma hk prime, another sigma, and then again expectation value with psi 0 prime. So the point is that whatever this sigma dot n hk prime times another sigma dot n, it's just some new operator, but it doesn't depend on theta, and it will be a new expectation value you can get for this more complicated operator, which I'm just going to call bk, and coefficient is sine square theta by 2. It will have expectation value of sigma dot n hk prime sigma dot n, whatever it is, that is bk. And then there is a third term which is proportional to sine theta by 2 multiplied by cos theta by 2, the cross terms. So yeah, so I can write it more explicitly where this is coming from. This is a psi 0 prime hk prime, so this is kind of expectation value of hk prime. This one is a expectation value of sigma dot n hk prime this expectation value are with respect to psi 0, and here there will be a third term which I will write it something which multiplied by cos theta by 2 sin theta by 2, and this quantity is a expectation value of I sigma dot, this has a positive term, yeah, and times this, so sigma dot n times hk minus hk and this looks more complicated, but it is still a Hermitian operator. Okay, take transpose, these two things get interchanged, but sigma and hk individually are Hermitian. The negative sign is taken care of by I. Okay. So now you have these three coefficients sitting over here, which are all expectation value of Hermitian operators. So they are real numbers. And that's as much as I need to know, because now I can rewrite these objects in many different ways just using trigonometric identities. So For example, I can write it as A cos theta plus B sin theta plus some constant. Then I can write cos square theta by 2 sin square theta 2. These things are converted to cosine sin theta and some constant. Because when you convert cos square theta by 2 to cos theta, you will get a 1 or some extra stuff. But the point is, all this complicated expression came down to a very simple trigonometric function. And that makes the job of optimization very trivial because I can minimize it. No problem. Don't have to evaluate any gradient, any complicated structure, can do it analytically. You can write it in different ways. So these thetas I was writing, they are all actually the theta j. So I did make the cutter notation cluttered, but that is what I won't bother to write it over here. But I started with r of theta j, so this is where the label appears. And so I don't know A, B, and C. Because they are all some complicated expectation value. So I have to actually run the algorithm and find out what A, B, C are. But how many trials do I need to determine ABC? I need only 3 measurements. There are 3 unknowns.
Three measurements at different theta length. 3 measurements at different theta length.
Yeah, different values of theta j. So I choose 3 different values of theta j, evaluate this expectation value with the job of the variational algorithm and determine ABC. Then I have a function which is now completely known. I find the best value of theta j. Because it's a simple trigonometric function with periodicity 2 pi. So and I can always find it's a sinusoid simple thing, where is the minimum. If I know the coefficient, I can completely determine it. What has happened? All the questions of changing the parameters slowly and finding the minimum have disappeared. I am not evaluating any gradients. Or whatever gradients I have to do, I will do it analytically. And I can write this version. This is actually a work which is initially not there in the Q-Skit version, but once the paper came out, they put in another error mitigation algorithm inside it, and the reference is archive 1903 12166. So how does the algorithm look like? That to get the sinusoidal function, so you need 3 values of theta j. Where are you going to put them? Well, you put them as far as you can, because it's going to thus give a sinusoidal function, and the farther away you are, you will have a better control of what the values are. So these people recommend choose 3 choices, which is theta 0, three values, some theta 0, some initial thing, put it plus pi by 2 and minus pi by 2. Why pi by 2? That's just to solve this equation kind of easily, because with pi by 2 shift, cos theta and sin theta get interchanged, whatever up to a sign. So you have a simple relation between A, B, C, and whatever the minimum value it will be, etc. And that's it. What you have done is, instead of using this small evaluation and incrementing theta by some small step to find the minimum, you have to use a large step. In a sense, the philosophy which was used in Grover's algorithm. Use large steps, find the solution, don't worry about evaluating any gradients. And now the full algorithm can be broken down into several steps. You have to remember that, yes, analytical values can be tried out, etc., but when you do the calculation, there will be noisy corrections to all those things. So whatever A, B, C you will get, they are not going to be some accurately fixed numbers. They will be up to some noisy errors. So the minimum value you get for theta is also uncertain up to that level. So the full algorithm works is, first step is parameterize this complete circuit. Which I wrote down here, whatever is the evaluation. Second is choose some theta j to optimize. Okay. One can do it randomly, but probably you can just go through all of them one by one in some sequence. Find its optimal value, keeping theta j or I not equal to j fixed. All the other ones you are not changing. You are changing only one of them. And then you, with 3 trials. And because it is going to be noisy, then you better keep that this will be another run. So one parameter you optimize, then you fix the value of whatever that is by running one extra run at that particular value, because it will include some noise. So you have to have the systems evaluation, whatever parameter you choose, go through all of them one by one, and that will minimize at one cycle, but all of them are not simultaneously minimized. Okay. So that is why at the end you go back and iterate. You run one cycle of minimization on all of them, then run another cycle by again going through the whole thing until you get the answer coming out stable. Okay. And this works extremely well compared to all the earlier things which people were trying with variational methods in terms of approaching this minimum value of the Hamiltonian quickly. extremely well is a difference again in orders of magnitude. And that is a useful point of this algorithm, that yes, you are using in a sense a large step algorithm when you are extremizing a particular expectation value. And if you can find such solution, they are always what you call robust. That is what I tried out, that there will be some quantum noise, but a small quantum noise will not perturb your result very much where your step size is large. So yeah, I will stop at this particular stage. There is an alternate version which these people also provided, is whether instead of doing all these things one by one, can I simultaneously tune all the parameters? Well, it can be done. You can again work out similar expressions, but doesn't help you very much. This one works as good as anything else. Or rather, it works actually a little bit better than simultaneous extremization over multiple parameters.
When we were tuning only theta j,
Yeah,
then all other theta we selected randomly and keep them fixed.
yeah.
Then using field trials at different theta j. So still the constant ABC remains the constant. Means this constant ABC don't depend on parameter theta j. Theta don't depend.
Yeah. No, that is why you have to cycle through all of them one by one. And it is not a simultaneous minimization with all the parameters. It's a minimizing one parameter while the other ones are still not necessarily minimized. Then you minimize the other parameters and the values keep on shifting every time. And that is why you need to iterate it till all the values stabilize and you get some desired convergence in the values. But it is in that sense an iterative procedure. The question is, does it converge fast? And in practice, it has been demonstrated that yes, it works very well.
Sampling cost, how big it is?
Well, you can ask how many terms you will need. If you have m qubits, m 1 qubit rotation, how many runs you will need? It will be 3 to the power m. Because 3 trials for every theta I. So the m of these angles, 1 qubit rotations, the total number for one cycle will be 3 raised to m. Then how many times you have to repeat it to convergence is a next level, but that numbers is probably not as large as 3 to the power m. 3 to, yeah. But so this is a 3 raised to
Number of cycles is linear in terms of
that will depend actually on the properties of the function and all those kind of things. But I have not said anything about what the Hamiltonian is. Some Hamiltonian may converge very fast, some may not converge so fast. There are other features which are related to that.
So if we talk about one qubit rotation, why this given angle decomposition 3 steps is most efficient compared to direct geodesic evaluation? That's why we desire this 3-step decomposition.
Because how many steps you want to use to 1 qubit rotation, only 3 finite angle rotations are needed. If you are going to do small steps along the geodesic, you will require lot many steps, and each one of them you need to control. And controlling a small number of large steps is much easier.
Means number of gates is here 3 and there are large number of gates.
Yeah.
So when you're talking about noise in this complex system, multiple sources, one could be the numerical errors as well that come because of the small
Yeah.
steps, and the other is also the device noise. So like especially for this optimizer, here I would be assuming that the profile is the same.
Yeah, so all those noises will be buried in this measurements of this whatever A, B, and C. It can have whatever imperfections on your device. Maybe it is an environmental noise, whether device imperfection, whether it is due to the control pulses which you send. They are all buried inside here, and they need to be controlled independently if you want the algorithm to be more accurate.
My question was in case those constants itself are dependent on time, and that's causing the problem.
Yeah, so that is not part of this algorithm. That will go in the earlier part, which was I was describing. There's a control and pulse shaping that you should use to cut down the noise of the device itself.
So I have to out in pulse shaping. So this pulse shaping technique is like scalable or not? How is scalable it is? Like here, 10 qubit illustration is given. Can be scalable?
Yeah, it's a scalable. I mean, the paper which I quoted is now gone somewhere. They actually did it up to the order of 10 qubit to find out how big a system they could handle, and it worked reasonably well. Okay. Of course, the more the number of qubits, this number of parameters you have to worry about, it all goes up. But if you stick that I'm only going to use this 1 qubit and 2 qubit gates, you can keep it as a polynomial as a good criterion for how many pulses you need to shape. The Hilbert space goes up exponentially. That you don't want to worry about. Yeah.
So once I have find out the shape of the pulse, the next time if I'm applying some other algorithm, the
Same pulse, yeah.
can be used.
Same pulse can be used. Yes. As long as the operation is the same, some logic gate, whatever it is, you have perfected it, you can keep on using it. And what they demonstrated in this Q control test is that the device noise in the IBM processors, it fluctuated day by day. But the shape pulses did not show that fluctuation. Okay, so it kind of indicated that the device noise remains whatever it is, fixed in direction but uncertain in magnitude. So the next day, some noise is there, but it is in the same direction. Magnitude has changed, but the pulse shaping kind of brought the magnitude down, and the same thing worked the next day.
So after some time, we need to calibrate this pulse.
Yeah. But the shape pulses require much less calibration or recalibration or anything like that.
In this case, pulse shaping is I we are not requiring more number of gates, more number of 1 qubit gates than 2n.
Because that is how you have designed your logic circuit. You started with implementing an arbitrary algorithm, but you broke it down that I can convert that algorithm to only a sequence of 1 qubit and 2 qubit gates. I don't need anything more.
Actually, these are different types of gates. Like you said, x and y on each qubit line, so it becomes 2n. But I'm asking about total number of gates. That might be
That depends on the algorithm, your problem. You want to implement a Fourier transform, well, you have to count how many of these gates you need. But the point is that Fourier transform can be implemented using only 1 qubit and 2 qubit gates. I don't need any other type of gates. And so whatever I want to optimize, I will optimize only those qubits which I am using in the circuit.
Here also 1 by 1. Here also 1 qubit. 1 by 1 gate.
As many gates as you need in your algorithm. Okay, this is a kind of maximum number. You are not going to have anything more than that. Your algorithm can be simple and it can use less number of gates. That's entirely possible.